So this screencast is going to be all about gases. So as you know, we're talking about the three states of matter. And I think it's important to just remember that all matter can move through the three states of matter, theoretically. So the easiest one to think about is just water. So if you think about solid water, we have a special name for that. We call it ice, right? And so when you start to heat up the ice, the molecules get enough kinetic energy. Remember that kinetic energy is the energy of motion. The molecules get enough kinetic energy that they break free of their solid state. They start to slide past each other or flow, diffuse, and become liquid. If we continue heating that liquid, we keep maybe the ice is on in a pot over the stove. As those molecules start to warm, they eventually then get hot enough that they have enough energy to leave the liquid and jump up into the gas state. When we talk about kinetic energy, we'll often make an analogy or a comparison to like sugar. If you have if you're very, very tired and you're very like still and sedentary, you're like a solid. And if I start feeding you sugar, you might get enough movement, enough energy that you start like kind of moving around. And then if you keep feeding you sugar, then you start to get way overexcited and you jump up off the couch and you're now running around the house. That's more of the gas state. So when we're talking about gases, we say that they are at the highest energy because they are the warmest. And remember, heat is energy in the form of kinetic energy is movement, but heat is energy. So if gases are the warmest state of matter, then they have the most energy. The space between them is the largest. They're the farthest apart, and they're the fastest moving. Because they have the most energy, they're the fastest moving. Because there's the most space between them, they are also the most compressible, meaning that you can smush them, you can squish them out. If what I just said was fast for you, the beauty of screencast is that you could just rewind it and listen again and make sure that that makes sense before we move on. So today we're going to do two long lists. And I'll be honest, even if you were in class, we would do the same long list today. Both of the lists that we're talking about are with respect to the kinetic molecular theory. The kinetic molecular theory tells us that all particles, all matter, no matter the kind, are always in motion, even solids. So we mentioned that before, that even solids are in motion. And one extension of the kinetic molecular theory is this idea of a gas called an ideal gas. Now, an ideal gas is like an ideal student. This is a student that doesn't exist, right? They do everything perfectly. They're always giving 100% effort. They're never goofing around. They're never taking the easy way out. They're always trying their hardest. Um, it's an imaginary gas, it's pretend. So we start out this whole conversation by pretending that gases are ideal gases, much like every day I start out the day pretending like my children are ideal children and like my students are ideal students. And then I deal with the times when they're not ideal later. But we start out with the assumption that they're ideal. So the first list is what is true if gases are ideal. So a perfect gas, okay, the fundamental assumptions, a perfect gas would have small, hard spheres with insignificant volume. I think you can imagine a gas as like one of those bouncy balls that you buy at the like at a grocery store or something, and they bounce all over the place. In the scope of a room, those bouncy balls are a small hard sphere with insignificant volume. Okay, they're so tiny that they don't even really matter in the room. It's not like, oh, well, I was going to walk in this room, but one of those tiny little bouncy balls is in here. I don't have a problem with that. So, gas molecules, as a result, are much farther apart than liquids or gases. There is mostly empty space around them. The second assumption of an ideal gas is that the movement of gas particles is rapid, constant, and random. Each one of these words is really important. Rapid is fast. So gas particles are always moving very, very quickly. Gas particles are in constant motion. They do not stop. They do not slow down. They're constantly moving. And lastly, their movement is random. Random movement means that they are able to change directions at any time. So they're moving in straight lines, but when they bounce off of something, there's no telling what direction they will bounce off. Third thing, third assumption of an ideal gas is that gas particle collisions are elastic. So when you hear the word elastic, you're probably thinking of like sweatpants, right? Like an elastic top. And what elastic means, so I think what helps is to think about what a perfectly inelastic collision, the opposite would be. Our cars are made to have perfectly inelastic collisions. What that means is that when two cars are coming together and they run into each other, they're supposed to stop right there. Crumple zones and engine mounts breaking and all sorts of things are made so that when two cars run into each other, they don't move, they don't involve any other cars. Gas particles are exactly the opposite. We say that when two gas particles come into contact, they bounce off of each other with exactly the same amount of energy that they came in with. The collision is elastic. So there is no loss of energy, not through heat, light, or sound. If you've ever seen the show Flubber or The Nutty Professor, or if you've played with the bouncy balls are close to an elastic collision. You know, if you bounce them, they're pretty close to being elastic, but officially they do lose some energy, right? Eventually, a bouncy ball will stop bouncing, but but they're close. Okay, they're a pretty close example of an elastic collision. Collisions between gas particles are elastic, but also collisions between the container wall. When the gas particle runs into the container wall, it also bounces off with an equal amount of energy. Okay, so gas particle collisions are elastic. So three fundamental assumptions: small hard spheres with insignificant volume. Okay, that means that the particle is super tiny in the huge amount of empty space that's around. The movement of the particles is rapid, constant, and random, quick, ever changing, never stopping. And gas particles collisions are elastic. There is no loss of energy. In addition to these fundamental assumptions of the ideal gas, we also have this idea that the uh, energy of a gas depends only on the temperature. So that means that at the same temperature, gas particles all have the same amount of energy. That means that smaller gases are moving faster and larger gases are moving just a little bit slower. And you can imagine that. So imagine you were at Costco, okay, and you were standing with one of those really big carts at Costco, and the cart was empty, and you shoved the cart and it goes rolling away from you, okay, pretty fast. Okay, now imagine you're at the end of your Costco trip and you're standing and you have your Costco cart and the cart is totally full because like COVID-19 is going on, so that everyone's buying all these crazy supplies. And you're standing there and you grab the ends of the cart and you push, and it wouldn't go very fast, right? Because it's so heavy that it's not going to move very fast. That's what this part is telling us. It's telling us that all gases have the same amount of kinetic energy at the same temperature. So not all gases are moving at the same speed. Okay, so bigger gases move slower and smaller gases move faster. Okay, these assumptions of the ideal gas bring us to what we know about how gases behave. So we have a list of things, of applications, things we know about gases because of the ideal gas laws, because of the the theories of an ideal gas. Okay, the first thing we know about gases is they expand. Because the gas particles are moving so quickly, they're going to spread out to fill the space of any room that they're in. The example chemistry books always give is about perfume. Okay, but the example I always give is about farting. What I want you to think about is if you are sitting and you fart, first you will smell it. right? It's near you. That fart smell, that gas fart smell expands out of your radius, right? And the people around you start to smell it. And then even a little further away, they start to smell it. And then eventually nobody smells it. Not because it's gone, but because it has expanded so far that it has diffused so much that it's no longer creating a scent. So that fart, once it's made, it stays in our atmosphere forever. You are totally breathing in farts right now. You just can't smell them, hopefully. Okay. Second application is that because gases are moving randomly, constantly, and quickly, rapidly, they're going to move past each other. The fluidity, gases form fluids, so they can move past each other without any hindrance, no forces of attraction between gas particles. Gas particles have a low density. Density equals mass over volume. I'm going to see if I can draw this for you. So the equation that we have for this is D equals M over V. Density equals mass over volume. Do you guys remember that? So the more mass you have, the more dense something is. The more volume you have, the less dense it is. So when you're talking about like styrofoam, okay, something like styrofoam has a small amount of mass in a really large amount of volume. Something like a weight, like a kettlebell, has a really large amount of mass in a really small amount of volume. So it would have a high density. So low density has a small amount of mass in a large amount of volume. That sounds like an Edpuzzle question to me. Okay, the last application of the ideal gas laws is compressibility. So because gases have expanded, because they are so spread out, that makes them very compressible. That means that you're able to put pressure on them and force those particles closer together. That's what compressibility means. And it really is the reason behind like a helium tank. So when you put helium into a helium tank, what they do is they take the regular helium gas and they compress it into a small amount of space. If you have a carbonator at your house, like a soda stream, that's compressed CO2 in that little canister. And so they take the gas and they compress it in there. If you have an aerosol of like hairspray, they take that gas and they compress it in there. And that's why when you open it, it sprays out, okay? Because there's so much pressure behind it. So you can compress the gas close together and then you can contain it. It doesn't like being contained. It will eventually burst out. That's why if you heat a can in the sun, right, like a spray can or something in the sun, it will eventually burst open because the pressure gets so high on the inside. I said that was the last one, but I was wrong. There's one more, and that's that gases can diffuse. And this is a part of the expansion. Diffusing is mixing. So if you have one kind of gas over here and you have another kind of gas over here, when they expand towards each other, they will mix. And that's what's going to cause diffusion, the mixing of two through their random motion. So you should be able to list this group. You should be able to answer questions about each one of these definitions. And as an extension of that, your next assignment is going to be about vocab. All right. That's the Edpuzzle for today. See you guys later.